Okay, the next part of this topic on the physical applications of calculus is all about the motion of a particle in a straight line. So really you're thinking about a particle moving up and down the x-axis. And we are going to ignore friction, gravity and other influences on the motion. And we can find the particle's displacement, velocity and acceleration at any time. There's a couple of new keywords in this topic which we're going to define over the next couple of slides. The particle can also be referred to as a body, or it can be even something quite large such as a car. So you can imagine a car moving up and down the x-axis. So it can really describe any moving object. So what is displacement? Displacement, we usually use the letter x to represent displacement, and it measures the distance of a particle from a fixed point, which is the origin. And unlike distance, displacement can be either positive or negative, according to which side of the origin is on. So if we have a number line here, and we have our origin here, if the particle is over this side of the origin, the displacement is positive. If the particle is somewhere down here, we say the displacement of the particle is negative, or it's to the left of the origin. Alright, when x equals 0, the particle is at the origin. Then velocity. We can think of velocity like speed, but unlike speed, velocity has both magnitude and direction. And it is a measure of the rate of change of displacement with respect to time. So you can think of it as being the first derivative of displacement. And sometimes you can see it in this notation, v equals dx dt, or you can also see it as in this new notation, x with a dot above it. So that's the first derivative of velocity. And it can be positive or negative depending on which direction the object is travelling. So if the particle is moving to the right, the velocity is positive, and if the particle is moving to the left, then we say the velocity is negative. And when the object is not moving, we say that it is at rest. And when a particle is at rest, that means velocity is equal to 0. Second derivative of displacement, or you can think of it as being the rate of change of velocity with respect to time. Alright, so there's a couple of different notations you can use for acceleration. You can either say it's a, or dv dt, or the second derivative of x, which is d squared x dt squared. You can also see it written as x double dot. Alright, so acceleration can either be positive or negative according to the direction it is in. So if a particle is, if acceleration is to the right, then you can say that acceleration is positive, and if acceleration is to the left, then you say acceleration is negative. If acceleration is in the same direction as velocity, then the particle is speeding up. So it's accelerating. This second bullet point here is a very important concept to understand. So if acceleration and velocity are in the same direction, then the particle is speeding up. And if acceleration is in the opposite direction to velocity, then the particle is slowing down. Okay, very important key point for you to understand. Alright, if the object is travelling at a constant velocity, there is no acceleration, because remember, acceleration is the rate of change of velocity with respect to time. So if you had something travelling at a constant velocity, so just say this was a graph of velocity versus time, constant velocity, there's a graph of a constant velocity. You can see the gradient of that graph is 0. That's why the acceleration is 0 if a particle is travelling at a constant velocity. Okay, so let's have a look at some other things that will be useful in this topic. And if you see the word initially, that means when at the start of the motion. So at the start of time when t equals 0. Obviously, t can only be greater than or equal to 0. T is never going to be less than 0. At the origin means the particle is at x equals 0. If the question says that a particle is at rest or stationary, that means the velocity is 0. And because we know that the particle is going to be moving in a straight line, then the particle is going to be moving, say, up to the right, and it'll stop momentarily and then move back. When it stops momentarily right here, that is when the velocity is equal to 0, and that also will help us to find the maximum displacement, or when the particle changes direction. Okay, and the maximum velocity occurs when the acceleration is 0. So it's kind of linking in everything you've learned in geometrical applications of calculus about maximum and minimum points. So the max, just because the derivative, the rate of change of displacement is velocity, you know that when you find the first derivative, that's when a stationary point occurs, and which can be a maximum or a minimum. So that's why this bit here, when you can find the maximum displacement when v equals 0. And similarly, because acceleration is the rate of change of velocity with respect to time, you can find the maximum velocity by making the acceleration equal to 0, because acceleration is the rate of change of velocity. If you were asked to find the distance travelled, then you need to take into account any journey and return. Okay, so just like how I set up here, a particle could be moving up to the right and then changes direction and comes back down. If the question's asking for the total distance travelled, you need to take into consideration that distance plus that distance. Okay, so distance travelled is always going to be a positive number. It can never be negative, unlike displacement. Displacement can be positive or negative depending on the location of the particle in relation to the origin. Average speed can never be negative as well, and we can just say that's the distance travelled over the time taken. So you know that if you were to draw a graph of distance versus time, then the gradient of that line is going to be your speed. Okay, so the average speed is rise over run. The rise is the distance, the run is time. Okay, let's have a look at a question, an example. The displacement from the origin x meters of a particle at time t seconds is given by that. Find an expression for A, the velocity, and B, the acceleration. So remember, the velocity is the rate of change of displacement with respect to time, dx dt. So let's just differentiate this. The derivative is going to be 16 minus 3t squared. Okay, and then for part B, acceleration is dv dt, or it's the second derivative. So we're just differentiating this now. And so differentiating that, you get negative 6t. Too easy. For example, a particle is moving along the x-axis so that its displacement after t seconds is given by this. Find the position of the particle initially. Remember, initially means when t equals 0, and after 7 seconds. So for part A, we'll first find the position of the particle when t equals 0, just by subbing in t equals 0. And you can see clearly up here, when t equals 0, you got that equals 0 and that equals 0, so x equals 5. So the particle is 5 meters to the right of the origin. 5 meters to the right. Whoa. Of the origin. It's very hard to write on these things. And also we had to find the position of the particle when t equals 7. So that is going to occur simply substituting in t equals 7 into the equation for the expression for the displacement of the particle. And we'll get negative 2 meters. So remember, negative 2 for displacement means the particle is 2 meters to the left, to the left of the origin. Alright, part B. Find when the particle is 11 meters to the left of the origin. So this question is asking us to find t. So find when means find t when x equals negative 11. So we're going to make x here equal negative 11 because it's 11 meters to the left of the origin. To the left of the origin is a negative displacement. And then we are simply solving this equation for t. And it's a quadratic equation. We'll move everything to the left-hand side. And negative 11 minus 5 is negative 16. We can factorise this quadratic equation quite easily because 8 times 2 is 16. And we're going to end up with 2 answers for t. T equals 8 or negative 2. Remember, this is time. Time's got to be positive, so we can rule out the answer of negative 2. And t is going to have to equal 8 because t has got to be greater than or equal to 0. Okay, we can't go backwards in time. All right, part C, find the average speed of P over the first 2 seconds of motion. So remember the formula we just had on the previous page for average speed was the distance travelled over the time. So let's find the distance travelled. Well, we already know that when initially the particle is 5 metres to the right. So let's find the displacement when t equals 2. All right, so when t equals 2, where is this particle? When t equals 2, we just need to substitute into our formula. X equals 5 plus 6 times 2, which is 12, minus 2 squared, and the particle is 13 metres. So initially it's at 5 metres, then we go to 13 metres. So our average speed is going to be our change in x divided by our change in time. Our change in x is 13 minus 5. Our change in time is 2 minus 0, which ends up being 4. And speed is going to have the units metres per second because the distance, the displacement, the units for that was metres. We have that up here. And we're talking about seconds here for time. So it's metres per second. All right, part D, the maximum displacement to the right of the origin. Okay, so remember the maximum displacement, the particle is moving up and down the origin. It's starting 5 metres to the right of the origin, it's moving up and coming back down. So how far up does it go before it turns around and comes back down? The point at which it stops and turns and comes back down, remember, is when the velocity equals 0. So then we can find when the velocity equals 0 and then substitute that time back into our equation to find what the actual displacement is. So given our expression we have for the displacement, let's see if we can use that to find an expression for the velocity. And we can quite easily, because remember the velocity is just the first derivative. Let's use a new notation there for velocity, x dot, and that means dx dt, so we're just differentiating this. So there's our expression. Now, max displacement occurs when x dot equals 0. I'm going to need a new page here. I'll see if I can insert one in the middle of a recording. Max displacement occurs when velocity equals 0. Yay, new page. Okay, so our expression for our velocity is 6 minus 2t. We're making that equal to 0. We're trying to find when this velocity equals 0. And solving this equation becomes quite clear that the velocity equals 0 when t equals 3. So the question, though, was to find what the maximum displacement to the right of the origin is. So we just need to now substitute that back into our expression for our displacement, which is 5 plus 6t minus t squared, because we know maximum displacement occurs when t equals 3. So let's substitute 3 there and a 3 there, and you get x equals 5 plus 6 times 3 minus 3 squared. So our max displacement ends up being 14 metres to the right. Alright, then the last part of this question is asking for the distance travelled during the first 5 seconds of motion. Now let's maybe draw a graph and see what information we've got already here. We've got that initially the particle is starting 5 metres to the right of the origin. So this is a graph of the displacement x versus time. Then we have that when t equals 3, we've got a maximum displacement at 14 metres. So it's going up to here at 14 metres to the right of the origin. And then we have 5 metres. The question's asking the distance travelled during the first 5 seconds of motion. So let's find where the particle is when t equals 5. So when t equals 5, what is the displacement of the particle? Because we know it's stopped and changed direction at t equals 3. So at t equals 5, it's on its way back to the origin, but how close is it? Well, we're just substituting into the equation for the displacement, and we see that it is 10 metres, positive 10 metres to the right of the origin. So we'll say 10's here. So our particle is about here. So if we were to graph this, starting at initially at t equals 0, the particle is 5 metres to the right. At t equals 3, it's 14 metres. And at t equals 5, it's back down to 10 metres to the right of the origin. So the total distance travelled, then, you can see, is equal to this 14 minus 5. So the distance when it's moving to the right, plus the distance when it moves from 14 down to 10. Okay, so you can see there's 9 metres when it's moving to the right, and it's moving to the left for 4 metres, so the total distance travelled is 13 metres. Alright, now on the worksheet that you've got, let's have a look at the first question there. We've got a graph of the displacement of the particle as it moves in a straight line versus t. So x is displacement, t is obviously time. When is the particle at rest? The particle is going to be at rest at the stationary points. Yeah, because at rest is, remember, is when velocity equals 0. Velocity is the first derivative. Okay, so it's going to be at rest at the turning points, which looks like it's going to be just here, up here at T3, and just down here at T5. Okay, T3 and T5. When is the particle at the origin? The origin is when x equals 0. So on this graph we've got x. So we've got 0, x equals 0 here, positive x values to the right of the origin up here, and negative displacements down here. That's when the particle's to the left of the origin. So at the origin is anywhere along this x-axis. So right there at T4 and right here at T6. Okay, so T4 and T6. When is the particle at the furthest point from the origin? So that's going to be when its displacement from the origin is the furthest. So remember, here's the origin. Going up here is moving away from the origin, and going this way is moving away from the origin. So is this point further away from the x-axis, or is this point further away from the x-axis? I think it's this point here, and that's going to occur at T5, because the question's asking when. Okay, so that's T5. In part B, is the particle moving faster at T1 or T6? Moving faster. So that's talking about its speed or its velocity. Remember, velocity or speed is the first derivative. Remember, the first derivative is the gradient function. So where is the gradient the steepest? Is it the gradient the steepest right here at T1 or right here at T6? It's very obvious that the gradient is steeper at T6. So it's moving the fastest at T6. How do you know? The gradient is steeper. And sketch the graphs of velocity and acceleration of the particle. So we're going to just sketch those on top of this graph. So I'm going to draw the velocity graph in red. Okay, so we're drawing velocity, which is the first derivative or the gradient function of the displacement. So whereabouts is the gradient 0? Well, we can see positive gradient is 0 here, negative gradient all the way down here, the gradient is equal to 0 just there, positive gradient going all the way up and then getting still positive but less positive. So let's first draw in our critical points or cheat points when the velocity is 0. The velocity is going to be 0 right here at the turning point and right here at this other turning point. Now remember, this part of the graph here, the gradient was positive, so our velocity graph is going to be above the x-axis. And we're starting from, what is the gradient initially? Initially just here, you can see the gradient looks like it's almost 0. If you were to draw a tangent on this curve, it would be almost very horizontal, so you can even have it starting there. Coming down here, next part of the curve, going from here to here, you can see the gradient is negative, which means the velocity is going to be negative, which means the velocity is going to be below the graph is going to be below the x-axis just there. And then we've got the velocity increasing. The gradient, you can see, is positive, getting steeper here and then getting less steeper, but still positive the whole way there. So the velocity graph is going to be above the x-axis, and as it's getting less steeper here, you can see that the gradient is approaching 0. So it's going to turn back around and approach 0. And it's going to probably turn back around and approach 0, where you can see right here, the concavity, it's getting less steep and approaching 0 there. So maybe we'll have it approaching right about there. Alright, so the red graph is our velocity graph, and then let's draw acceleration, our graph of acceleration in blue. So now acceleration is the rate of change of velocity, so we're drawing the second derivative. So whereabouts is the velocity have turning points? Well, that's where the acceleration is going to be 0. So it looks like we have a turning point around about here and around about here. So that's where we're going to put in our turning points of 0 and 0. And it is also roughly a turning point about here. Alright, this section of the graph from here to here is positive gradient, has a positive gradient, so acceleration is going to be positive. So going above the x-axis, so something like this. Next section of the graph from here to here, has a negative gradient, so it'll be below the x-axis. The next section of the graph from here to here, you can see the gradient is positive, so above the x-axis. And then the next section of the graph, you can see going from where here to down here, the gradient is negative and it's getting less negative and it's approaching 0, the gradient of that graph. So our acceleration is going to be negative and then it'll approach 0. So the blue graph is the sketch of the graph of the acceleration of the particle. Alright, also on the worksheet, another graph showing the displacement of the particle, and we need to sketch the graph of its velocity and acceleration. So I think you should probably maybe pause the video, have a go at this, and then see if you're correct. Alright, so we are I'm going to graph the velocity in 0 again. So our turning points line up with right there and right there. This section of the graph here is a negative gradient. So our velocity is going to be below the x-axis, like this. This next section of the graph has a positive gradient going from there to there. So our velocity will be above the x-axis. And the next section of the graph has a negative gradient, which means our velocity is going to be below the x-axis. So that's the one in red is our velocity graph. And then in blue I'm going to draw the acceleration. So right there is turning point, acceleration is 0 just there. This section of the graph, the gradient is positive, which means the acceleration is above the x-axis. In this section of the graph here, the gradient is negative, so acceleration is below the x-axis. So the blue graph is acceleration. So that's a review of, sketching the gradient function that we did in calculus at the end of last year. Last example, a particle has displacement given by x equals cos 2t to find the find the equations of velocity and acceleration and sketch these graphs. Okay, so velocity is going to equal the derivative of cos 2t, which is 2 sine t, and remember the derivative of the derivative of cos is negative, so it'll be negative 2 sine t. And the acceleration is the derivative of negative 2 sine 2t, so the derivative of 2t is 2 times by 2, negative 4, and then goes back to cos 2t. Alright, then we have to graph these. So, a bit of revision of trig. The velocity graph there, the period is going to be, the period is going to be the same for both of these graphs, 2 pi on n, where n is 2. So the period is going to be pi. And the amplitude for the velocity, you can see the amplitude is 2, and the amplitude for the acceleration graph is going to be 4. Alright, so if we were to graph these, what would we have? Let's have a look. We are graphing time over here. And let's draw one period, so up to pi. This is going to be pi on 2. And this would make it half of that, which is pi on 4. 1 pi on 4, 2 pi on 4, 3 pi on 4. Alright, our velocity is -2 sine 2t. So remember, sine is normally starting at 0, but because this is -2t, it's going, instead of going up first, so you know, sine curve normally goes like that. Well, because this is the negative, it's going to be going down this way first, and it's going to go down to have an amplitude of 2, and it's going to have a period of pi, so we need to have one cycle and finish here at pi. So it'll be like that, and wherever we go down to, we'll make that equal to 2. So that value there would have to be +2, and this value down here would be -2. Okay, and then we need to also graph the acceleration, so I probably should have done the acceleration equation in a different colour. So we'll say acceleration, there we go. So we're graphing this cosine curve, cos of 2t, the period's the same, and remember cos normally starts at 1, but because this is 4, we're starting at 4, but because it's negative, we're starting down at -4. Alright, and it's going to go, let's draw our dots, it's got to go, let me do a quick trace, something like this, and finish back down here at -4. So that is going to be our x-intercept. Up here at pi on 2, it's going to go all the way up to 4. 3 pi on 4, it's going to be down to 0, and pi, it'll be back down to -4. So there's our graph of the acceleration of the particle. Okay, and maybe let's label those graphs as well.